is Cody, also from Northeastern, and he will talk about learning to reheat with random matrix theory.
All right, thank you very much, Fabian, and thank you very much to the organizers for putting together this wonderful meeting. Hopefully you can pay attention to my talk, even though there's a wonderful view right to your right. So this is based on work with Jim Halverson, Brent Nelson, who are both here, as well as Brent's student Gustavo, who is fantastic. And this is really two talks put together, but in a related way. The first bit of the talk is going to inform the second part. And so really, the way you should think about this title is it's learning to reheat with random matrix theory. So that is the correct pronunciation. So Jim already gave a nice introduction to the landscape, but let me say a few more words about the, at least some lower bounds on the exact size. So the string landscape is the enormous set of vacua, or geometries, solutions, effective field theories, however you want to think about it, that arise in compactifications of string theory on compact spaces. So the size of the landscape is actually unknown. There are some evidence that at least in certain corners of the landscape, such as F theory, that the number of these vacua is finite. But let me tell you about some of the numbers that are continuously changing as lower bounds increase. So first off, there's a lower bound due to my own work with Jim and Ben Sung of 4/3 times 2.96 times 10 to the 755 on the number of geometries for F theory. And Yunan and Wadi, through Monte Carlo methods, estimate this number to actually be around 10 to the 3,000. So there's an enormous number of geometries for F theory or string compactifications. In addition, you can put flux in these geometries to actually find vacua, and the typical string geometry is expected to support around 10 to the 500 flux vacua, and some up to 10 to the 272,000. So I'd say it's probably impossible to enumerate all the vacua to study global properties of the landscape. So we need a different approach to understand what is possible in string theory. So our current approach is general theorems and conjectures about quantum gravity and string theory, coupled to ensemble studies to actually learn what is there. The latter can be used to refine, refute, or support no-go conjectures, or go conjectures if you have them, about things like de Sitter solutions, super Planckian field ranges, the weak gravity conjecture, etc. And both approaches are likely necessary to understand, to gain a global understanding of properties of the string landscape. So if we want to study ensembles, we have to understand what sort of things we can actually construct. And there are many large ensembles of compactification data available. The first is Kreuzer-Skarka database of 4D reflexive polytopes, from which you can get 3D Calabi hypersurfaces to construct string vacua. And these were classified by Kreuzer and Skarka to be about 473 million polytopes. And the number of triangulations is estimated to be about 10 to the 10,505 due to work of people here using machine learning to estimate these numbers. There's the aforementioned tree ensemble of F3 bases, which I mentioned in the previous slide. There's the skeleton ensemble by Wadi Taylor, Yunan Wang. Sorry, Yunan, I just gave it a title. I don't know what you actually want this thing to be called. There's the complete intersection Calabi-Yau's, there's heterotic orbifolds, and this is just to name a few. So there are many, many different ensembles one can study to actually get your hands dirty and see what's out there in string theory. However, even with these ensembles, the size of the data in these ensembles is prohibitively large to actually do a complete brute force scan. In addition, there's good evidence that most effective field theories in string theory have a large number of fields, whether it be Kähler moduli or complex structure moduli. I'll concentrate on Kähler moduli because that's mostly what my talk is about. So in the F theory base that's thought to house the largest number of flux vacua, well, this thing is 98 Kähler moduli. Our tree ensemble, well, a typical geometry has about 1,000 Kähler moduli, and in Kreuzer-Skarka, well, the largest polytope, which is thought to have the largest number of triangulations, has 491 Kähler moduli. So one often finds oneself in the regime of large numbers of fields. Theories with large n are difficult to deal with. See Jim's nice talk. And we therefore expect we will be able to understand fewer examples at large n systematically. We won't be able to scan over as many of them because it takes longer to understand each one individually. So we can instead take a statistical approach. We can study the ensembles well enough to develop some sort of model, some sort of statistical model at small or moderate n of the relevant physical quantities, and then we can extrapolate such a model to large n and see what we learn. So the effective field theory parameters in the landscape themselves define a distribution. So if we can accurately model this distribution, we can study the statistics of the landscape. So we can ask some interesting questions about frequency of interesting events, such as large effective axion decay constants, large field ranges, ultralight axions, numbers of standard models, de Sitter solutions, etc. We can study the stability of typical critical points and inflationary trajectories, and we can ask if there's correlations between seemingly independent physical quantities in these convectifications. So we could take the statistical effective field theory approach, take the parameters in the effective field theory to be random variables drawn from some distributions. There are many ways to do this, but one such example is to take this Lagrangian for a scalar field and take the parameters such as the kinetic matrix, the mass matrix, and various couplings to be randomly drawn from ensembles determined by actual string data. So a general parameter in such a random effective field theory is some sort of random tensor. It has some indices. And the two index tensors are A, especially important to understand, and B, the starting point to understanding more general random tensors in the string landscape. The two index ones I have in mind are KAB, which is the metric on field space. It determines the kinetic term. It's important for inflation, axion physics, counting flux vacua. And MAB is the Hessian, and the eigenvalues are essentially the masses of the theory. And of course, in a candidate vacuum, you'd want to check that all of these eigenvalues are positive. So if I have these two index objects, a random model of these is naturally a random matrix theory. So in a random matrix theory, what I do is I draw the entries of the matrix randomly from some fixed distributions, which I'll call omega. One reason that random matrix theory is powerful is universality. There are certain properties that are independent of n, such as the shapes of some spectra. So we can plausibly learn something at smaller n and extrapolate to larger n to learn something about the landscape. So today I'll focus on the Kähler metric, this kinetic term for Kähler moduli in type 2b as an example. So let me give you an introduction to some of the data. Well, if we compactify type 2b on an orientifold of a Calabi-Yau threefold X, well, the n equals 1 supersymmetric data contains this Kähler potential. K is equal to minus 2 log v. V is the volume of the internal space measured by this Kähler form, J. And it can be written in terms of these triple intersection numbers, kappa, I, J, K, and these parameters T. These parameters T are the expansion parameters of your Kähler form. The good coordinates on Kähler moduli space are complexified Kähler moduli, the real parts of which parameterize the volumes of 4 cycles in the internal space, which I can again write in terms of these little t's and these intersection numbers. And these are counted topologically by h11 of x, this Hodge number. So this is just some number. It's essentially counting holes in the space. And then I can define my Kähler metric on the space by simply taking derivatives with respect to the Kähler moduli. This 1/4 is because these variables are the real variables. So the geometric data to actually determining this kinetic matrix on Kähler moduli space are the triple intersection numbers and the Kähler cone. So these parameters can't just take any value. You have to enforce that all your volumes in the internal space are positive, or correspondingly, all the eigenvalues of your kinetic term are positive. So in 2014, along with Liam McAllister and Paul McGurk, we initiated a systematic study of such Kähler metrics in type 2b. So we came up with a triangulation algorithm. This is before more robust triangulation algorithms were developed that allowed us to extrapolate even to further h11. This allowed us to study hypersurfaces in torque varieties of h1 about 25. And so we started studying the statistics of this kinetic matrix for Kähler moduli, and we found some interesting properties. First off, it tends to be heavy-tailed, which you can roughly say as the largest eigenvalue tends to be much, much larger than the bulk. So I have some plots of this. This is just a simple example at h1 equals 15, so 15 moduli, where the smallest eigenvalues tend to be around 0.1, and the largest points out, well, even past 800. I cut this plot off to make it a little easier to look at. Second, the components of the Riemann curvature tensor have correlations. And this Riemann curvature tensor enters into computing the mass matrix for these Kähler moduli, which I'm not going to go into any further detail. So, can we actually construct a random matrix model that reproduces the correct spectrum? Well, there are some simple guesses one could take to actually start to try to construct these random matrix models. The first is a Wishart model. I could simply take K is equal to A transpose A for some real matrix A, where I draw the entries of A from some normal distribution, omega. However, this does not actually reproduce the correlations in the Riemann curvature, nor does it reproduce the heavy tails for at least reasonable choices of omega. One can also try inverse Wishart, so basically 1 over Wishart. So if you have small eigenvalues of Wishart, you have very, very large eigenvalues of inverse Wishart. This can help reproduce the heavy tails that we saw, but doesn't help with correlations in the curvature tensor. Okay, so we can be a little more sophisticated. We could try taking a Kähler potential of the same form that we know exists on Kähler moduli space in type 2b. So we could take K is equal to minus 2 log V, where V is written as this volume form, or I just draw these triple intersection numbers from some distribution. I take this thing to be a random, totally symmetric tensor. So this actually has a problem in that the associated Kähler cone, or the space in which the matrix is positive definite, tends to be empty when you take these triple intersection numbers to be completely random. So there exists no values of these little parameters t such that the Kähler metric is positive definite. So this doesn't seem to work either. So we have to think a little harder, and we have to put in some constraints to actually make this thing positive definite. So one way to do that, partially based on the work of Ferrari, Klotzoff, and Zeldich in modeling these random matrices, is to use random Bergman metrics. So let me consider a Kähler potential of the form log f of z and z bar, where z runs over all my holomorphic coordinates zi. Now let me take f to be some vector z or s bar contracted with this positive definite matrix p alpha beta. So here, S is a basis of polynomials in Z of less than or equal to degree less than or equal to k, where k is some fixed integer. And really, these are holomorphic sections of a line bundle. P, I said, is a positive definite matrix. So the general idea here is that we're actually going to take our moduli space, the space that we're trying to model the metric on, compactify it, and then we're going to put it in projective space. So we're going to allow this to be some either hypersurface or some complete intersection in projective space. Yeah, Sven.
So, what was the motivation to exactly use that ansatz? Because this ansatz, right, comes from
Yeah.
talking about phenomenology.
Exactly. So a naive motivation is that, listen, the Kähler potential that we know exists on Kähler moduli space has this log form, and this log form allows us to take into account correlations in between the different components of the metric and the curvature tensor. So using a log was motivated by trying to understand how correlations work. However, there's another nice property of these Bergman metrics, is that the Bergman metrics actually can approximate all Kähler metrics. This is a theorem of Tian, Yao, and Zeldich, where they showed as you take the number, the degree of this polynomial to go to infinity, you can approximate any Kähler metric you want. The way you should think about that is you're using these Bergman metrics as algebraic approximations to a Kähler metric from embedding in projective space. But independent of that, you can actually approximate anything with it. So it's actually a very, very powerful thing. So the name of the game in approximating a given metric is understanding these sections S and this positive definite matrix P. So an arbitrarily precise Bergman metric always exists. If P is positive definite, I can in general write this thing as A dagger A for a complex matrix A. In our case, we'll take A to be real just for simplicity. So our goal in understanding random Bergman metrics is to model this matrix A. Okay, so how do we actually construct a random matrix model that reproduces the Calabi-Yau data that we want? Well, first we have to gather data at small to moderate H11 to get some sample distribution that we want to model. Next, we design a random matrix model that fits this data, and then we can extrapolate this thing up to large H11 to try to learn something. So what we're going to consider, as we considered in the past, is Calabi-Yau threefold hypersurfaces in toric varieties. The way you get this data is you first choose a polytope from Kreutzer-Skarka, you triangulate it, and then you can examine the triangulation to obtain the relevant geometric data, which includes the Mori cone of the toric variety and the intersection numbers of X. So we use packages such as Sage and Topcom, and we can use a FRST method, a triangulation method, due to Andreas, in which a triangulation of an arbitrarily polytope takes about 30 seconds. And then we can gather the data really fast. So along with Liam and his student Mehmet, we've started to build up a database of such hypersurfaces and such hypersurface data in order to be able to study things at large H1. So, how do we actually construct the random matrix theory? Well, given the moduli space metric data, we want to produce such a random matrix theory that actually gives you this data, that can reproduce the Calabi-Yau data. So let me tell you the game we have to play. Well, we'll consider these Bergman metrics, where defined by, so the basis is fixed. I just write down a basis of polynomials in Z. So the name of the game is to determine this matrix P. If P is positive definite, in general, I can write it as A dagger A. And I'm going to draw these A's from some normal distribution. Each entry of A I'll draw from some unique normal distribution with some mean, mu, and some standard deviation, sigma. So our goal is to determine these distributions such that they reproduce the metric data that we have gathered. In general, this is a hard problem. There are many parameters, and the relative behavior of the variables as you scale n, or even just for fixed n, is not entirely obvious. So this, yeah, go ahead.
So you pull back the Fubini-Study metric to get the distribution you want to fit this to?
No. So I'm not going to actually embed this ever. I'm just going to gather Calabi-Yau data, look at the metrics, create some distribution, and then fit this matrix so that it reproduces it. I actually compute this in general. So for many examples, I compute the intersection form, I compute the Mori cone, and then I gather an ensemble of metrics by enumerating over geometries and exploring the Mori cone or the Kähler cone. So this is really example driven. I'm actually going to use reinforcement learning to try to construct a random matrix model that reproduces the data that we already have. So I have many parameters. I have a large state space. And so this is a really good candidate game to try to use machine learning for. So while supervised machine learning predicts given some data, reinforcement learning explores and searches a state space to try to solve a problem. The most famous examples, as far as I know, are AlphaGo and AlphaGo 0. So what happens is an agent interacts with the environment. It perceives a state from the state space, and its policy picks and executes an action given just the state. So the agent arrives in a state and receives a reward depending on what the state is. Successive rewards accumulate into a return, and the return might penalize future rewards via a discount factor. You don't want this thing to have to explore for too long. And the policy is optimized to maximize a reward. So the agent's going to explore, and it's going to learn how to act based on a game, based on rewards that I tell it. The implementation, well, model-free RL, we want algorithms that work regardless of the environment we choose, regardless of the type of game we want to play, so we can use CS-implemented algorithms. So we'll use 3 modules. OpenAI, due to Elon, defines what an environment is and how to interface. And ChainRL provides the actual reinforcement learning algorithms and the neural net architecture that is used. So all we do as physicists is provide the environment, which in general is maybe 50 new lines of code to these already existing packages. So it's very quick to actually get your hands dirty and to start playing these games. This algorithm, which is A3C, that I'm going to use, asynchronous advantage actor critic, is very nice because it runs on parallel CPUs, and I don't necessarily need GPUs to play this game. So, reinforcement learning for random matrix theory, the game. So in general, we have many parameters, but I'm going to try to do the simplest model possible that might actually be able to reproduce the Calabi-Yau data that I have. So what I'm going to do is I'm going to fix the means of each of these entries at 0, and I'm going to draw each column from an independent distribution, each column in this matrix A. And what I'm going to do, the game is to allow the standard deviations of the entries of each column to vary. So a move is to simply vary the standard deviation. Take one step in some direction, and it changes one of the standard deviations. And then we sample an RNT model, given these distributions, and we get the actual moments of the distribution that the reinforcement agent finds. The goal is to reproduce the moments of the Calabi-Yau data. Now the reward, well, I want to tell it that it should get closer and closer to Calabi-Yau data. So the reward is 1 over the distance squared, where the distance is in moment space. I take the squared sum of the difference in the moments from the distribution that I have from the reinforcement learning agent minus the distribution of the actual Calabi-Yau data. So as it gets closer and closer, the reward gets greater and greater. And the game over is when I reproduce the moments accurately enough, which I can define to be within some percentage. It has to be close enough. There are further details. You can weight the moments by importance by putting some coefficients in here if you think one moment is more important, especially when you have finite data. The higher and higher moments are going to be measured less and less accurately. You can vary the number of draws that the agent takes. You can change the parameters of the agents, et cetera. So there's still much to do here. This is very initial results, but I think the initial results are quite promising. So let me just show you a single example from H1 equals 15. So I took H1 equals 15, and this is the moduli space metric data from 200 Calabi-Yau hypersurfaces at this number. I'm going to try to reproduce the first 3 moments using reinforcement learning. So this didn't appear that great, but this is a log plot. So the number goes from -3 here, 10 to the -3, to 10 to the 2 here. The Calabi-Yau data is in beige here, and the null RMT model, which I took to be the initial moments 1 over square root of n, square root of h11, gives this gray spectrum here. And this is a log plot, so this is actually quite far off. So I let this agent train for about 24 hours, and it varied the moments to go from 0.25 to between 0.1 and 0.35 for the various entries, with a step size of 0.0025, so 0.001 times the initial moments. And what it did was it actually reproduced the moments of the Calabi-Yau data very, very well. So the initial distance it started off with was about 10,000, and it brought this down to about 0.03. So you can see this in the spectrum on this log plot is basically took this, this null model and moved it over to the right a little bit while still reproducing this left tail very, very well. So this trained RMT model did much, much better than null data. It's not perfect, obviously. It needs to get peaked up a little bit in the middle, but if you actually look at the moments that I asked it to reproduce are fairly close. So I'd say these are promising initial results, but we could tweak the game to improve it. We can change the parameters a little bit. We can allow for longer training times. We can allow the means to vary as well, or the individual, not just the columns, but the rows to be drawn from different distributions, which would change the game and increase the complexity. The short, yeah, please, a couple questions, yeah.
Are you going to tell us some things about how well this extrapolates if you do this at one H11 and ask about a higher one, or if you do this with one sampling of the Kähler cone and extrapolate to another sampling of the Kähler cone?
I would love to tell you that, but I'll probably tell you that in a future date when I know the answers to those questions. Okay. That's certainly a work in progress. Yeah.
Do you have an explanation as to why it overpredicts on the right?
No, but my intuition is that I haven't allowed the parameter space to be big enough. So it's able to pull the right tail over, but it's not able to then vary something else to peak it up. So I imagine my hope is that if I allow the means to vary, perhaps, that maybe this will allow for it to not overpredict on the right so much.
And does this seem to happen for other experiments that you've done?
Yes, it does, but I haven't showed you any plots. Yeah. So I've looked at smaller H1 as well. For H1 equals 5 and 10, the problem is that then, it's a random matrix model, so 5 and 10 are not that large of n, as 15 isn't either. So that's all I'm going to tell you about these random matrix models. But now I want to ask a specific physics question that I'm going to eventually apply this method to. So let me talk a little bit about reheating and string theory, just the order 0 questions about reheating. So these compactifications I told you about tend to come with a lot of extra stuff beyond the standard model, including many, many hidden gauge sectors. So the question is, after inflation, which sectors get reheated? Where does the energy go? Well, if we reheat the hidden sectors too much, we might overproduce dark matter, and this would be a problem. It's important to ask this in string theory, as this may possibly rule out a large number of string compactifications. If a generic large N string compactification overproduces dark matter, well, then it's not a good model of the universe. So there's been some very nice work at small h11, but as most string compactifications come with large h11, we need to understand reheating there as well. So we're going to study we're going to ask this question in the largest known ensemble of F-theory geometries, This is still in an exploratory phase, but I think we're learning a lot of interesting things, so I want to tell you about them. So let me tell you about these geometries that we're going to study. These are topologically distinct F-theory geometries in a connected moduli space, and they have some nice universal features. So we're going to study threefold bases for F-theory. We're going to study them at generic complex structure. So the 7 branes are the ones determined at generic complex structure, and these are so-called non-Higgsable clusters. Our starting point is going to be a weak Fano threefold B, for which the generic vibration is smooth, so there are no gauge groups to start with. And then we're just going to start blowing up the base. So we're going to start doing topological transitions, which is going to force some gauge groups upon us and change the number of moduli. So we can do this ad hoc an infinite number of times. We can just keep blowing up. But we're going to demand that our geometries are all at finite distance in moduli space from one another. The reason being is A, well, if you start with a geometry that you understand the physics of, and you can move to another geometry, you expect to be able to understand the physics there too, if you can move there in finite distance in moduli space. So we can then actually classify the number of blowups we can do, and this is some finite number, which I'll tell you more about in a minute. And then the ensemble we have is all the different ways of performing these blowups. So if we're going to do a large number of blowups, well, the geometry that's going to give us the largest number of, the starting geometry that's going to give us the largest number of total geometries in the ensemble is the one with the largest number of stuff we can blow up. And this turns out to be the polytope, the torque variety with the largest number of torque points. So if we consider this polytope, it's a big one. Any fine regular star triangulation of it has 108 edges and 72 faces. So we have 72 torque points that we can blow up. And then we're just going to start blowing up. We're going to start doing these topological transitions. And if we count the number of possible blowups we can do that are independent and keep us at finite distance in moduli space, well, there's some simple combinatorics that give us a number of 2.96 times 10 to the 755. So this is just that integer written out. It's kind of cute to put on the board sometimes. And of all the polytopes, all the initial starting points from which to do these blowups, this starting object dominates by a factor of 10 to the 60. So this is really the largest set determined by this initial geometry. So these geometries have some nice universality properties in terms of the physics, in that most of them, a very, very large fraction of them, have non-Higgsable 7 branes. And we can read off the gauge groups of these things quite easily just from the combinatorics of the of the polytope. So pretty much all these geometries have some factors of E8 to the 10 times F4 to the 18 times some gauge groups that depend on the actual blow-up properties. So a typical geometry in this ensemble has order 1,000 axions, order hundreds of gauge sectors, each supported on some torque, on a divisor, not a torque curve, excuse me. We expect very little matter in these ensembles. So there are many pure Suzy-Yang-Milne sectors that should generate gaugino condensates from moduli stabilization. And we find that the axions in these theories tend to be light and have relatively flat potentials. So they're therefore good inflaton candidates. So we're going to study reheating in axion inflation in these geometries. So let me just write down the most general Lagrangian for the theories that we want to consider in this simple analysis. Well, we have a canonically normalized, a set of canonically normalized axions. We have some canonically normalized gauge fields, then we have some couplings between the axions and the gauge fields determined by Ci alpha. Alpha runs over the gauge fields, I runs over the other fields. So let me ask a very, very simple order 1 question. If an axion inflaton couples to a gauge field, how much does it necessarily couple to other gauge fields? So this will tell us if we reheat into one sector, how much do we necessarily dump energy into other sectors as well? Well, that's the order 1 question. I'm going to simplify this a little bit just for the purposes of getting our feet wet and understanding some statistics early. Let me ask an order 0 question. Let me take the inflaton, the axion inflaton, to be pointed along a single gauge group G1, which just means I'm going to choose one of these gauge groups, and I'm going to let the canonically normalized field out front of it be the inflaton. That linear combination is the inflaton. So I can write this interaction Lagrangian over here as minus C inf times phi inf times F1 plus the rest of the stuff in the spaces. And so the rest of the stuff generically will contain factors of phi inf as well. So I want to measure the relative size of these coefficients. So given C inf, what is the ratio of Ci, the couplings to other gauge fields, over C inf? So let me study this in a large number of examples. Well, I actually have to write down this data. So in type 2b in F theory, well, I start in a different basis. I start with some general Kähler potential. I start with these Q matrices, which tell me these couplings to the gauge fields. So this kinetic matrix is determined by this Kähler potential, minus 2 log v. And let me say that since I'm working in F theory, I'm taking minus 2 log v to be a model. So I'm modeling the actual Kähler potential in F theory by minus 2 log v, which we know is a good approximation in string theory. So this is a model just to try to start to understand reheating in F theory and string theory. These matrices Q are determined by the 7 branes wrapping various divisors in internal space, which determine the gauge groups. And the different gauge group you get is determined by the Kähler fibers and the corresponding elliptic vibration. So at the end of the day, I have this Lagrangian that I can write down from string theory. And this data can be computed at moderate H1 for many examples. So what we'd like to do is the same idea as in the first part of the talk, understand it at moderate to reasonably large H1, come up with some model, and then extrapolate to large H1 to learn something about the landscape. So to actually compute the ratio of these couplings that I want to compute, good. So let me now take O to label the other gauge group, the other thing that I'm reheating into, and I to label the inflaton gauge group, the thing that I'm trying to reheat into. So I want to write down this actual data, and so we have to go through this procedure of actually building up all the geometric data, writing it on the effective field theory, which, I said a little bit about this. We have to compute triple intersection numbers, compute a point in the Morley cone, blah, blah, blah. There's a lot of stuff you have to do. Thank you. And at the end of the day, you can actually write this coupling, these ratios of couplings, in quite a simple way. So if di is the divisor that supports the inflaton gauge group, and do is the other divisor that I'm trying to measure the relative coupling strength with, well, I can define this coordinate x alpha beta, which is the volume of the intersection of the two divisors, d alpha intersect d beta, divided by the product of the volumes of each divisors. And then I can write CO over CI as XIO plus some non-local factor, 1 over V, divided by XII plus 1 over V. So let me actually go ahead and start computing this thing. Well, if I compute this in a null model, and a null model is something where I'm taking all this data, the Kähler metric and the Q's, these couplings, to be drawn from some Wishart distribution, well, I get the spectrum on the right of CO over CI. Kind of peaks around, this is a log plot, so kind of peaks around 1 or 0.1 here, and then falls off to 10 to the minus 4 over here. This is in the null model, so this is just one model for a null effective field theory that one might consider. But if we go ahead and compute this stuff in F theory and string theory, well, the spectrum looks different. There's a little bit of a tail to the right where there's some very, very large ratios of couplings. But most of these things peak at 10 to the minus 10. So most of these things are actually very, very small. So you're seeing relatively small ratios of couplings. You really do couple more to the sector you intended to than other sectors. So this study suggests that the couplings are more preferential than in the null model. So the question is, can we understand the associative physics and extrapolate to large numbers? Well, this is the thing that we want to understand, the CO over CI, defined in terms of these complicated variables here. And what we have here is some local piece, local in the sense that it depends on the actual intersection between the two corresponding divisors. And then we have some non-local piece, just some global 1 over V thing that, whose interpretation isn't entirely clear at first. So the question is, what is the physics and geometry determining the ratios of these coefficients of these numbers? Is there some simple underlying structure? And the answer is yes, and it's actually fairly easy to solve problems like this using a neural net. So there's a very nice package that allows you to build up neural nets in Python. And so we employed such a neural net, a feed-forward neural net, where we took the data that we found and we tried different combinations of variables being fed into the neural net. And the question we wanted to ask was, which variables actually determine the physics? Because if the neural net can predict to very high accuracy on a smaller number of variables, well, you can conjecture that those variables are the actual ones determining the physics. And we found was that we found very high accuracy, very, very high accuracy predictions training on only these x's and not the non-local piece. So we found was only this local piece matters. So this is just the output, and really I just want to show you this mean square error going down as a function of time. It starts at about 60 with an untrained neural net. It doesn't know what it's doing, and then it trains very, very quickly. This was an order of about a minute to very, very, very high accuracy. So these local things, XIO and XII, predict this ratio of couplings to very, very high accuracy. And in fact, the relationship is about that they're equal. So CO over CI is approximately, to very high accuracy, XIO over XII, which then if you go through the algebra, you can write as this ratios of volumes of the intersection of the two divided by the self-intersection of the inflaton divisor times some bit that depends on 4-cycle volumes. So what this means is, well, this whole picture is local. If an axion inflaton is oriented along a particular gauge group, which corresponds to a divisor in the internal space, it's only going to significantly couple to things that are very, very close to it. So it's only going to couple to gauge sectors supported on divisors that intersect the inflaton divisor non-trivially. So in my toric picture, well, the toric divisors correspond to points, and the intersections correspond to little lines between the points. If this is my inflaton divisor in blue, it's only going to significantly couple to these divisors here in red, where I can draw a line between the blue dots and the red dots.
The bottom left should also be red.
Sorry? Oh, the bottom left should be red. Thanks, Mom. Yeah. And what we find is CO over CI tends to be small regardless of the choice of DI and DO. So I can flip I and O. I can flip the corresponding, the two different gauge groups and still find a small coupling. So it's really determined not so much by this non-symmetric piece, but by this symmetric piece here. So what's actually going on here? Well, it's the curve volumes that seem to be determining this, the sizes of these couplings. So what we find is that the intersection between two distinct divisors in these geometries tends to be much, much less than any self-intersections. So these self-intersections are computed using linear equivalences. And in our examples, and this is particular to our examples, there are 3 linear equivalences, and what we learn is that they're actually dense. So if I write these 3 extra divisors as linear equivalent to a sum of a basis of divisors, well, I can write them in terms of these rational coefficients here. And what we find is these coefficients are never 0, and they're order 1. So I can then flip the process on its head, and I can try to compute the self-intersections using these linear equivalences. And what I find is that the volumes of these self-intersections tend to be on order of the sums of all the other intersections. So this gives sort of an explanation as to the plots we're seeing. Well, we have some inflaton divisor here, and our ansatz is that it's going to couple strongest to the sector that corresponds to the largest curve of intersection. So if this divisor, this is DO, and this is DI, and if DO intersect DI is the largest, we suspect it's going to couple preferentially to that sector. And actually that's what we find is true in examples. So here's just one single example where I plotted log 10 of the ratio of these Wilson coefficients. Well, this is a log plot, so here's 0. And so I find that there's 2 divisors that are relatively, there's 2 gauge groups that are relatively strongly coupled. The inflaton gauge group that I intended to have the strongest coupling to, and then one other thing which corresponds to this curve. The full details, of course, well, I'm telling you something about curve and divisor volumes, so the full details actually depends on what the curve and divisor volumes are. And what we showed with Mehmet and Liam was that there actually tends to be a very large hierarchy in these curve and divisor volumes. So actually, to understand the full story, we need to understand these Kähler cone structures better. So the gauge groups that are simultaneously reheated are determined by topology, by these intersections to at least order 0. And we can actually, for the most part, determine these gauge groups by local data. So let me take an example of SU2, and let me just ask the question, if I attempt to reheat into SU2, if I take this to be my inflaton gauge group, what do I reheat into, what else do I reheat into generally? And so I can go through this ensemble. We took about 1,000 of these geometries to do this initial study. And we found was, well, you reheat it a little bit into E8, but you mostly reheat into G2 and SU2. And this is consistent with the topology. Every single SU2 divisor in our ensemble actually comes along with a G2 divisor, which it intersects non-trivially. and 90% of SU2 divisors intersect with another SU2 divisor. On the other hand, 10% of SU2 divisors intersect in the E8 divisor, which is completely consistent with the plot that we're showing here. So this is work in progress. So the neural net allowed us to identify important variables in the axion reheating problem and suggested a nice geometric interpretation. And this gives us evidence for preferential reheating, or at least preferential distributions of these couplings in a large ensemble of examples. So this is good progress, I'd say, would be a statistical study of reheating, where we can do these explicit calculations. But really, really good progress would be to understand this at some finite number of moduli and then be able to extrapolate out to the rest of the landscape, or at least the rest of this ensemble, to understand even larger n. So both the statistical study and development of the RMT model via both reinforcement learning and our own efforts as humans is work in progress. So let me sum up. The landscape is large. Most effective field theories seem to occur at large n. It's hard to deal with directly. And a statistical model, such as random matrix theory, allows us to study statistics of the landscape globally if we can develop such a model. So the initial, let's see, so examples of interest include moduli space metrics, these Wilson coefficient ratios that I talked about, and there's many more. Our initial results in the first part of the talk suggest that reinforcement learning can learn random matrix theory models to fit Calabi-Yau data. And then we want to try to apply this to a different problem, which was axion reheating. Well, we found some evidence in an ensemble for preferential couplings of axions in string theory that will be relevant at the very least for reheating. It might not determine the full picture, but these couplings are certainly going to be there. And the neural net allowed us to identify the most important variables and gave us a geometric interpretation. So now what we want to do is understand how to model these variables and use RMT to study the landscape as a whole. And this is currently in development, developing such an RMT model for the variables xi, or xio. And that's it. Thank you.
Thank you very much, Cody. Other questions?